Hi everyone, welcome to CS 2088 exam session 8, and today we'll be going over the solutions. So I'll assume you've read question 1, so let's start with A. So what they're asking us is fill in the circles corresponding to all values of probability y equals spam, for which the bag of words with these word probabilities will give spam as the most likely label. So this will take some math, so let me write it up here. So what they're asking is, for what values of probability y equals spam is it more likely? So when is it more likely that probability y equals spam given our word 1 equals perfect and our word 2 equals note? When is that more likely than predicting that y equals ham given w1 equals perfect and w2 equals note? So we can rewrite this using the naive Bayes structure. So this will factorize into the probability of w1 equal perfect given y equals spam, we'll call that s, times the probability w2 equals note given y equals s, and the probability that y equals s. So this is kind of the value that we're going to want to estimate. These are what the multiple choice values are for. And it's greater than, it's going to be the same exact decomposition, just with y equals h. So I'm low on space, so I won't write it out. So now we look in our table and we fill in these values. So probably w1 equals perfect given y equals spam. That's 1 over 8. So it's 1 over 8. We also look up probability w2 equals note given y equals spam. And this turns out to be 1 over 6 times probability y equals s. And when is this greater than, so we probability w1 equals perfect given y equals ham. So that's going to be 1 over 12 times probability w2 equals note given y equals ham, which is 1 over 8. And the probability that y equals ham is 1 minus the probability that y equals spam. So now we have an equation with only probability of y equals s. So if we do the math, this is detailed in the solutions, we'll get that probability of y equals s is greater than 1 over 3. So that's when we'll classify it as spam. So now we can go to our solutions, and anything greater than 1 over 3 we bubble in. So all of these. Cool. So now for B, you're given only 3 emails as a training set. Fill in the circles corresponding to the values you would estimate for the given probabilities if you were doing no smoothing. Okay, so this is basically doing counting. So probability that w equals sir given y equals spam. So we look at spam, there's 1 sir. And how many words? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 1 over 13. I look here, I don't see it, so none of the above. Given y equals ham, how many watches are there? So there is 1 watch. And how many words are ham? 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 9. I don't see 1 out of 9, so none of the above. Alright, given ham, how many gauntlets are there? There are none, so it's going to be 0. And what's the probability that y equals ham? Well, there's 2 ham emails and 1 spam, so it's going to be 2 over 3. Okay, so now on this part they're saying you're training with the same emails as in the previous question, but now you're doing Laplace smoothing with k equals 2. There are v words in the dictionary. Write concise expressions for each of the following. So first let's write the original probability. So the probability that w equals sir given y equals ham. So given y equals spam, how many sirs are there? where there's going to be exactly 1. If we look up here, and how many words are there? Well, we did this before. It's 13. So I'm adding k equals 2. So I'm adding 2 artificial samples. So on the denominator, I have to add, for all the words v, I'm adding 2. So I get 2v. Now we do the same thing, probability w equals watch, given y equals ham. So I found the original probability was 1/9. Now I add 2 artificial samples, that's what Laplace smoothing does, plus again 2v. And for probability y equals ham, well, I'm just adding the word likelihoods. I'm adding like more artificial samples of the words, but the number of emails, spam, and ham stays the same. So probability y equals ham is still going to be 2/3. Okay, so now let's look at question D. So on the holdout set, you see the following accuracies for different values of k. So there's the holdout set. Now on the training set, the accuracy for k equals 0 is 0.8. Fill in the circle of all plausible accuracies for k equals 10 on the training set. So let's just go and eliminate some of them. So if the training for k equals 10, the accuracy is 0.1, that's lower than the holdout set. And so this doesn't make sense because you should always do better on the training set than on the holdout. Now let's look at 0.99. So without any Laplace smoothing, on the training set we did 0.8. Now they're saying that with Laplace smoothing, we're actually doing even better. Now this also doesn't make any sense because the Laplace smoothing is adding artificial samples that are incorrect. So it shouldn't help us do better in training because Laplace smoothing is supposed to help bring up the holdout set. So now if we look at 0.7, so what we can see is actually now we need to look at how, looking at k, how does it affect the holdout accuracy? So we can see it goes up, 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 and then it goes down. So we can see is that Laplace smoothing at k equals 10 is actually hurting. So by a little bit. So we can see that on the training set, well, it was 0.8 without any Laplace smoothing, and with Laplace smoothing it goes down a little. So this seems reasonable. Okay, so now on to question E. So I'm assuming you've read it. So what we're doing is we're adding these new edges to increase the expressiveness of our naive Bayes model. So with the vocabulary consisting of V words, what is the minimal number of conditional word probabilities that need to be estimated for this model? Okay, so we basically need to look at the sizes of these conditional probability tables. So for a single W, it depends on its previous one, on W1, for example, and also on Y. So let's say Y is fixed. Then for W2 can take on V values, and W1 can take on V values. So that's going to be V squared entries. Because for a fixed value of W1, there's one conditional probability table that has V entries. So for all W1, which has V, then we have to have an V entries for W2. So that's V squared. Now that was assuming Y is fixed, but Y can take on 2 values. Therefore, the answer is going to be 2V squared. Okay. Now the next question says, select all expected effects of using the new model instead of the old one, if both are trained with a very large set of emails. So let's start with the easier ones. So does the accuracy on the training data, should it be higher with the new model? Well, yes, it should be, because our model is more expressive. It represents a larger set of distributions. Therefore, since we have a very large set of emails, basically we're able to approximate the distribution, the entries in the table correctly, then we should do better. The accuracy on the held out data should be higher with the new model. Again, because we have a very, very large set of training data, and the model's more expressive, so we can fully train the model with good entries in the probability tables, again, it'll be good. Now the first one. The entropy of the posterior should on average be lower with the new model. So this is not true. So now let's see why. So in the original naive Bayes, it looks something like this. So here we have less edges than in our new model. So because we have less edges, this is the same as saying making stronger assumptions. And when you make stronger assumptions, that means your estimates, your model is going to be overconfident. So our new model up here is actually less confident because we have more edges. And the less confident you are, the higher entropy you'll have. So it says lower, but you actually have higher entropy. Okay, so now we're going to work on question 2, which is a particle filter question. So we're basically trying to track where Waldo is. So I'll assume you've read it. So now for question A, they ask us to fill in the table below with the distribution of Waldo's location at time t equals 1. So since Waldo can only move one spot, we can use our prior plus the transition distribution to estimate where Waldo is. So what's the probability that where will Waldo be at xt equals 1? Well, so the probability that Waldo goes from, well, let's say he goes from A, given he's in B, times the probability started out in B, plus the probability he was in A and stayed in A, given that he was in A. So we can fill this out. What's the probability of A given he was in B? So probability of moving upstairs is 0.3. What's the probability he was in B at the previous time step? Well, that's given by our prior 0.2. So probability if he's in A, stays in A, that's 0.8. And what's the probability he was in A already? 0.1. So if you multiply and add, you get 0.14. So now we're going to do the same thing. So what's the probability we're in B at x1? Well, it's going to be the probability we end up in B given we were in A times the probability we were already in A plus the probability we were in B and we stayed there given what's the probability we're already in there plus the probability we got to B from C times the probability that we were already in C, or we were in C at the previous time step x0. So probability of B given that I was in A is going to be 0.2 times the probability of A is 0.1 plus probability I stayed, which is 0.5 plus the probability I was in B already was 0.2 plus probability I went up, which is 0.3 times probability I was already in C, which is 0.3. So I get 0.21. So we'll do the same thing. What's the probability that I got to C because I came down? So basically that I was in B, plus probability I stayed, plus probability that I went up. So probability I went down is still 0.2. Probability that I was in B was 0.2. So probability I stayed times probability I was already in C plus probability I went up well, I was in D, so probability I went up is 0.3. Probability I was in D was 0.4. So this turns out to be 0.31. And for D, so what's the probability I came down? D given C times probability of C plus probability that I stayed. So the probability that I came down is, let's see, 0.2 times probability I was in C, which was 0.3, plus the probability that in D I stayed, which is 0.7, and the probability I was already there, 0.4. So that equals 0.34. Okay, so now for part B, they say f tau of x is a fraction of time steps Waldo spends at position x from t equals 0 to t. The system of equations below solves for how long he spends in A, B, C, and D as a fraction. So fill in the blanks. So when we're filling these out, we notice that we want to basically find the stationary distribution. So we want to find out what is the value for f infinity, all of these. So that's going to be going on the right side. So what is f infinity of A? Well, the weighted sum is going to be the probability from each of the fraction of time. So if I'm in the fraction of time of A, what's the probability that from this fraction of time I stay there? Well, that's from the probability, so probability of A given A, so that's 0.8. Now, given that my fraction of time in B, what's the probability that I end up in A after being in B? Well, it's 0.3, and I cannot reach A from 0 in D. Now we do the same for f infinity of B, f infinity of C, f infinity D. And there'll be one more equation that we'll need. So from B can only be reached from A, B, or C, so not from D. So from A, what's the likelihood we go from A to B? Well, there's an incoming probability of 0.2. So the probability we stay is 0.5. And what's the probability we go up from C is 0.3. Now for C, we can't reach it from A, so that's a 0. Plus probably from B that we go down is 0.2. We stay with probability 0.5, and we go up with probability 0.3. And from D, that cannot be reached by A or B. If you're from C, there's a 0.2 probability that you would go down in D, and there's a 0.7 probability that if you're in D, you would stay in D. Now we also have a requirement that this is a fraction, which means that the sum of all the fractions of time, so the fraction of time I'm in A, B, C, and D, has to sum to 1. Okay, moving on. Now we have a sensor, so we're going to have observations. So I'll assume you have read it. So in part C, they say you decide to track Waldo by particle filtering with 3 particles. At time t equals 2, the particles are at positions x1 equals A, x2 equals B, and x3 equals C. Without incorporating any sensory information, what is the probability that the particles will be resampled as x1 equals B, x2 equals B, and x3 equals C? So this is just doing the time elapse, so it's the individual multiplications. So the weight, or the probability, will be the probability that x3 the particle that the new x1 prime equals B given x1 equals A, the probability that the new x2 prime equals B given x2 was B, and the probability that x3 prime equals C given x3 was C. So we know from before that the probability that if I'm in A, I go down, that's a 0.2 probability. And for the B and C, the probability that I stay in the same place is 0.5. This equals 0.05. Now let's say, to decouple this from the previous question, assume the particles after elapsing are as follows, and we observe the following for the roof sensor and the basement sensor. What are the particle weights given these observations? So the particle weights are the multiplications of the observations because the observations are independent. So the probability that our roof sensor equals plus S, given that we are 1 away, times the probability that our basement sensor equals negative S, given that we are 2 away. So now we can look at our models up here. So for roof and for basement, and if we plug in dr equals 1 and dB equals 2, we get out and multiply them together. Well, we can plug this in more directly. So given that dr equals 1 and plus S, it's going to be 0.3. And for the basement, given 2 and minus S, that'll be 0.6. So that equals 0.18. So we do the same thing for C. So we the probability SR equals plus S, given distance to the roof equals 2. The probability that SB equals minus S, given the distance to the basement equals 1. So given dr equals 2 and plus S, that'll be 0.6. And given minus S by dB equals 1, that'll be 0.3. So 0.18. And for the last one, we have the probability of SR equals plus S, given dr equals 3. And the probability of SB equals minus S, given dB equals 0. So given dr equals 3 and plus S, that'll be 0.9. And for this one, the probability SB equals minus S, given dB equals 0, is 0. So that gives us 0. Now, to decouple this from the previous question, assume the particle weights in the following table. What is the probability the particles will be resampled as x1 equals B, x2 equals B, and x3 equals D? So first, we say, what is the probability that we draw x1 as B? Well, it's going to be, well, we see that, so what we do is we take the probability, or how many, we sum up all the weights of x is equal B, we divide by the total sum, luckily these sum to 1. Now what's the probability that x2 equals B? Well, sum all the weights with x equal to B, it's 0.1, over the sum of all the weights, it's 1. And probably x3 equals D. Well, we sum all the weights with x equal D, so 0.3, there's only 1, over the sum of all the weights. So if we multiply this together, this is the probability.